estimating probabilities, right? Like that is essentially linear or logistic regression is a method to estimate probabilities in a certain way that is nice in some way. But before you can say what is good or bad in estimating probabilities, you got to answer some fundamental questions like this one: what is better? Or I phrased it as what is worse, right? So if the true probability is 55% and you estimate 59%, versus the true probability is 95% and the estimate is 99%. So in both cases, it's a difference of 4%. Let's see what you guys said. I want to reveal answer. Do I have to scroll to the bottom? Okay. All right. So pretty split. 3 people think scenario 1 is worth. That's 55 to 59. 2 people think it's 95 to 99, and 1 person thinks they're about the same. So I will tell you, in the way that is used for logistic regression, they are not about the same. One of them is much worse than the other. One of them is a lot worse than the other. So in the way that is used for logistic regression, they are not close. So it's either scenario 1 or scenario 2, and you guys have to pick. You should talk to your neighbor and see which one you think would be better. So think about what is the difference between the two. Maybe you want to write something down. Maybe you want to imagine some experiment. We'll think for a few minutes and we'll come back.
You would say, okay, this is 9%. So the person would be if the amount was more or overestimating. This is my reason.
I think the answer is other one. Because like
try to think of the logistic regression.
All the logistic regression that goes from 0 to 1. And like you know how it's
like I don't know what
there's a that's like one portion 0 and 1. So like does that make sense?
Yeah, you mean that
because 95 and 99 are like much further.
So you mean that the result will be changed from 0 to 1 probably? You mean like this? No, because it came to my mind after your explanation, and then we put the end.
Yeah.
If it is more probable, the result will be changed from 0 to 1. The person agrees.
Maybe something similar. I'm not sure the proper way to explain it, but something like that. Basically, I think if you change that it's like more influential. The way I would explain it, I don't know like what the former definition.
Yeah, you're right.
You make a judgment, it's almost around half.
So, shall we vote again?
Yeah, so I opened it up again, so you can put in your new vote if you want to change your vote or keep it the same. But if you scroll down to the bottom, there should be a new version where you can put in your vote. And once people have voted, we'll discuss as a class which one you guys think. Oh, is it making you input both? Like I know there's like a second part. Just put in a garbage answer for the second one, and we can. I'll give you another chance to think about that one. Okay, so should we discuss? Does someone want to explain why they support one position or the other position? Let me see, what did people say in the revote? Okay, now everybody is saying scenario 2 is worse. So it looks like you guys are reaching a consensus. Can someone tell me why scenario 2 is worse than scenario 1?
But the number of participants decreased.
Yeah, so some people didn't put it in, but that's okay. Maybe some people are, I should have made an option for it, I'm not sure. But yeah. Okay, so can someone tell me why they think scenario 2 is worse? Maybe somebody who switched. Is there anybody who switched from 1 to 2? Yeah.
You know, at first I thought if the percentage increase, the change in the percentage in percent would be less.
Ah, okay.
So this is a general idea if you are speaking about numbers. But when talking with James, I understand that if we go to the tail of the logistic regression, so there is going to be a much more, let's say, significant change from 0 to 1, for example. So this is the reason I changed from 1 to 2.
Okay, yeah. So I like what you said at first, right? It's like at first you were like, well, the change is 4% in both cases, and you were looking at the like relative change.
Yeah.
Right, relative change. Right. So for scenario one, that's like 4% divided by. I guess you have to decide if you're going to put 54 or 59, but it doesn't matter which. Let's do 54 versus scenario number 2, which is 4% divided by 94%, 95, 55.
59.
Yeah. So if you do this like relative change metric, which sometimes people use in real life, then the 55% one is worse. And yeah, I think you're right. This is not what logistic regression is doing. And so the thing you said is it had something to do with that curve. Is that what you're saying? So this is the logistic regression curve. Okay, and then so 95 to 99 is like something over here. 95% to 99%. There are two numbers that are near the top. And 55 to 95 are something here. I'm going to give you some colors. Did I do something wrong? Oh, I wrote the wrong number. Yeah, okay. I didn't do that. Actually, I didn't make one of the numbers the opposite of the other number on purpose. This is a coincidence. Okay. So 59%. So you're changing from here to here in one situation, and the other one you're changing from here to here. Something like that. Okay. And so what was your reasoning that this is a bigger change? Like
more significant from 0 to 1.
Yeah, this is great. I hadn't thought of explaining it this way. This is very nice. So the vertical change in both is 4%, but because the curve is steeper, the horizontal change is small here, and the horizontal change is big here. Horizontal. So the way I was thinking about it is equivalent to this, but is not as nice and visual, which is when you use this curve, you're changing from probabilities on the y-axis. On the x-axis, there's a simple word that people use every day and sometimes in Las Vegas to describe probabilities. So of course, if you have a sigmoid curve and you know where you are, you can figure out the probability. And mathematicians use probabilities. This is what people on the street use to describe random events.
Luck.
Yeah, luck, or odds. And actually, more specifically, I think that this is log odds or something. So the sigmoid function you can think of as just a transformation from two ways of describing random events. Probabilities, which we know, and you can also describe them as odds, right? And actually, this is the log odds. So if I say log odds of 10, if the log odds are 10, that means the odds are e to the 10, right? Because we're mathematicians, so we use e. And if the odds are e to the 10, that means that I have to sort of try e to the 10 times before it happens once, right? So it's something like it's like p over 1 minus p is e to the 10. So if you think about it this way, then these events of 55% and 95%, instead of thinking of them as probabilities, if you think about them as odds, then the difference becomes more clear. So let me write out scenario 1 and scenario 2 in terms of odds. So scenario number 1 was 55% to 59%. Okay, and 55%, the odds are about 2. They're not exactly 2, right? So if it was 50%, that would be 2 to 1, right? Because you would do, or I guess they're 1 to 1 odds, and you have to weight. So there's 2 ways to do odds. You can say 1 to 1 for 50%. You can say 1 to 1. And I guess the way we're doing it, the log odd, this is how we're doing it, right? Because the 50%, the log odds, or what I'm calling the sigmoid, is 0. If you have a sigmoid of 0, it's 50%, right? It's exactly in the middle. So this is e to, so the odds are e to the 0. So I'm thinking about this number 1. So it's like something to 1, 50% is 1 to 1. What is 55%? It's 55% to 45%. So what are the odds in the way I'm doing it are, I think 55% over 45%. So they're like 1 and a bit. I guess let's just estimate this. So 10, 1.2. If someone wants to do it more carefully, they can check. Something like that. So a little bit. And then the odds for 59% are 59% divided by 41%. This is like 1.5 or something like that. Should have checked these on my calculator. But they're both like a little bit more than 1, right? Like they're both, from the point of view of the odds, are a little bit worse than 1. On the other hand, if you do 95% to 99%, now there's a big difference, right? Because you have 95% divided by 5%. This is the odds. The odds of this are 18, 19, right? 19. And the odds for this one are 99% divided by 1%, or 99. So these two are both numbers about a little bit more than 1. This number is you're going from like 20 to 100, right? And so another way to think about it is how many trials you have to do until it happens. If something has a 55% chance or a 59% chance to happen, you sort of have to wait maybe like 2-ish trials to happen. 2 is this number plus 1, right? So you wait you try it 2.5 times. On average, it's going to happen. And this is also about 2 and a bit times. So like how many times do you have to try an event until a 55% or a 59% chance happens? It's like 2-ish times, a little more than 2. 95 to 99 is a huge difference. If something happens 95% of the time, then it's happening once every 20 times. That's like if you did it every day, it's like once a month. Where if 99% is every 100 days, that's like once every quarter. So there's a huge difference between these two. Yeah.
Isn't it a way where it's like every 1 in 20 days it won't happen?
Well, I'm saying how many times you need to try until it happens once on average. Oh, you mean, okay, I guess until it doesn't happen, until you miss. Yeah, okay, that's good. Yeah, thank you. Yeah, okay. Well, so I guess you could replace this with 5% and 1%. And it should be, you could do the 1 minus, it should still all be the same. And mathematically, the way this is expressed is that likelihood that was in the video. So I'm going to give you the likelihood formula now from that video. Let's do it over here. So yeah, I really like that visual with the sigmoid. That was great. But the formula, the likelihood, and this is called the cross entropy loss, which is coming from the likelihood. It's minus the log likelihood. So it's this formula. I'm gonna write no hats first. It's like this. With a minus sign. And some of the p's, either inside the log or outside the log, have a hat on them. And you always have to remember, is it the ones inside or not? And the way I remember is the thing on the outside, the true probability could be 1 or 0. And that would be fine. If the true probability was 1 or 0, we could estimate the probability is 99% and it's actually 1. Okay, that's a good estimate. The reverse, is really bad, right? If we estimate that it's a 100% chance and it's actually a 99% chance, we think it always happens. And if it even doesn't happen once, then like we're like completely wrong. So the thing inside the log, that is the p hat, and that is because you are not allowed to estimate p hat of 100% or 0%. You should never do 100% or 0%. Another way to say that is the sigmoid never actually gets to 100% or 0%, right? So this is the formula from the videos, and we can use Desmos now if you have the formula to evaluate. So did I do that on here? Let's make a new Desmos. Okay, so let's make p the true probability. P, that was 55%, 0.55. And let's look at the formula, which is p times the log of x plus 1 minus p times the log of 1 minus x. And so this is the curve. This is the curve. And of course, it lives between 0 and 1. It lives between 0 and 1. And you can see what happens when you slide p around. So when p goes between 0 and 1, this is how we measure the loss. And you can see it's this funny like asymmetrical thing, right? It's not like the square loss. So up until now in the course, we've talked about the square loss. And that is symmetrical, right? For the square loss, a difference of 4% is always a difference of 4%. But for the cross-entropy loss, it's asymmetrical. And okay, what were we wanted to look at the two scenarios. So let's call this f of x. We wanted to look at the situation where p was 55%. Is that what it was? Let's get the question right. P is 55% and p hat is 59%. So that would be f of 0.59. So that's negative 0.67. So scenario 1 is negative 0.69. Oh yeah, I guess I'm plotting negative this, so the loss isn't 0.69. And scenario number 2, what is the loss? Oh, it occurs to me something might go wrong. That'll be exciting. Let's see what happens. So I'm gonna put a 95 and 99, right? That was the other situation. 95 and 99. Okay, so this one I got 0.23. So here I can do x equals. So there's one spot. That's one of them. And then the other spot was 0.59. And okay, let me do a P2. What's a good letter for? Let's make Q. Okay, and let's color code everything. So let's make these two blue. And we'll make this one red. And red. Okay. So those are the two curves. Scenario 1 is this red curve. That's the curve we're measuring. And scenario 2 is this blue curve. And if you actually measure the actual log likelihood, the actual loss function, you get 0.69 and 0.23. So it looks like actually scenario 2 is better, right? And scenario 1 is worse, right? So it's the opposite of what I said. But there's another way of looking at it, which is interesting. Here, there's one more important difference between this loss function and the squared loss. Let me do the squared loss so you can see what that looks like. And let's do x minus 0.5 squared. So that's what the squared loss looks like. So the blue curve is very asymmetrical, it lives between 0 and 1. The green curve, that's the squared loss, is symmetrical, but it has another nice property, which is that it touches 0. The log likelihood function has a minimum that is not 0. So when you're doing the squared loss, you can get to 0, right? You can get 0 loss. But the log likelihood, this like cross-entropy loss, it has a minimum which is not 0. Even if you get it perfectly right, like even if the true value is 55% and you say it's 55%, you still get the peak of this curve. So because of that, you get funky stuff like this, which is that it seems like this measurement is better. This is really just because estimating something that has a 50% chance, even if you get it right on, you're going to still get half the coin flips wrong, right? So even if you're perfectly estimating a 50% coin flip, you still get a lot of them wrong, just because 50% is more random sort of than 99%. So the right way to measure it would be to do f of 0.99 minus f of p, and g of 0.99 minus g of 0.59 minus g of q. So to measure the difference, how far down you go. And if you do it that way, then really scenario 1 you'll see is a lot better than the other one. So this is the absolute loss was 0.69 and 0.23, but if you do the relative loss, the change from maximum, I'll say the change from minimum, then you get scenario number 1 and scenario number 2. What are the two numbers? One of them is G is 0.59. This is 0.03. And the other one is 0.04. So you can see scenario 2 is a lot worse. You're doing a lot worse than the best possible than scenario 1. So this is the relative. This is sometimes called, if you get for people who've seen some machine learning stuff, this appears sometimes, this is called the Kullback-Leibler divergence, the DKL, is the difference between the minimum. So it's the loss minus its absolute minimum. We might do some stuff with this later on in the course. There was a question at the back?
Oh yeah, I think it's fixed. I wanted to talk about like negative log.
Right.
This graph is gonna flip or?
Yeah, so I'm plotting the log likelihood, and the loss function is negative the log likelihood. So it's exactly this minus sign here. So if you want to think about it as a loss function is how much you lose, how much you get hit on the head by a newspaper for being bad. Like you did it wrong and you're bad. So you want to make the loss function as small as possible. You want to make the likelihood as high as possible. So there's a negative sign between them. And so it just depends on how you plot it. Here I did everything with an, I guess, upside down. If you want it as loss functions, they should be flipped. I don't know which way to, I think you kind of gotta know both. Because sometimes they come up one way or the other way. Yeah, that's a good point. Yeah, and I think I've made that mistake hundreds of times, forgetting the minus sign, so it's good to watch out for. Any other questions about this one?
I want to be clear.
Yeah.
I didn't really get it, but so what we are saying is that the scenario 1 and the 2, it depends.
So I guess it depends on which way you're looking at it. If you want to look at the absolute value, then the thing about scenario, like the absolute value, what it's actually telling us, let's go back to the actual thing here. Let's go to the, in scenario 1, if the true probability is 55%, and you're measuring success by how often I'm able to accurately guess the next outcome. So like imagine it's coin flips, and your job is get the next coin flip correct. Like you say it's heads or tails, just get it correct. In scenario 1, you're not going to do very well because it's 55%, you estimated 59%, so you're going to say it's always heads, say. You classify a p-hat of 59, you say, okay, heads. And it's going to be heads 55% of the time. So you're wrong 45% of the time, and you're right 55% of the time. That's kind of what this is telling you. You're sort of like how often you're actually correct. In the second one, it's a coin flip that's 95% of the time heads. So when you say it's heads, you're going to be right most of the time. And so the fact that this has a lower absolute loss is telling you that you're more correct in scenario 2 than scenario 1 when it comes to guessing what coin will come next. The thing I was trying to set up in this problem is which is a worse mistake in terms of estimating the probabilities. And in terms of estimating the probabilities, estimating 99% when it's actually 95% is a worse mistake because you're doing 0.04 worse than the best possible you could do. Whereas estimating 59 when it's actually 55, you're doing 0.003 worse than the best you could possibly do. So if you measure it relative to the best you could possibly do, then this is a much worse mistake than that. If you're trying to just say like how often you get the coin flips right, then scenario 1 is that you're screwed because like it's just a very random coin. Yeah, that's a very good question. Yeah.
So generally speaking, reaching the tails
Mm-hmm.
in all situations would be risky to me because
Yeah.
either the real value is far away from the tail, so you made a mistake, or if it is the real value is near the tail,
Right.
so you should be very careful.
Yes. So yeah. So I think maybe part of the point is that things get very distorted near the tails. So the square loss is kind of the same everywhere, like we did for linear regression. But once you start talking about coin flips and things are very nonlinear, especially near the tails. Yeah. So you got to be careful. I do think this is the right way to look at it because you can't control if someone gives you a coin and says please estimate. You can't control how the coin actually is, right? But you can control how good your estimate is. And so you can try to like make it better or worse. And again, when you're trying to minimize, right? If someone says please minimize, it doesn't matter if you minimize the absolute or the relative, like you're still minimizing. But I think you should think about it this way, right? Like there is some true value, and we're trying to get as close to the maximum as we can. Yeah. So all of these things, they all have interpretations as log likelihoods, which means that if you do e to the power of these, you're seeing like how much worse you're doing than you could. If you do e to the power of these numbers, you get that's like you multiply the probability or the likelihood. That's how you do it. Okay. The other one is quite tricky, so let's skip the other one. This one, scenario 3 and scenario 4, the point I wanted to make is that 95% to 99% and 99% to 95%, they are different. So this formula on the board is not symmetrical. The p hat and the p's are different, right? And the p's are on the outside and the p hats are in logs on the inside. So these two numbers will actually be different. I don't have a good way of knowing which is worse. They're like my intuition, I don't know which one's worse. They both seem bad, but you can plug it in and find out. So if you plug it in and find out, one of them is worse, and we can do that in Desmos. So here I'll set the P to 95, and I'll set the Q to 99, and we wanted this function 95 minus Q, and over here we want 99 minus P. So this one is 0.04. So when the true probability is 95, you're doing 0.04 worse. And then on the other one, you're doing 0.02 worse. So according to the math, in some sense, the situation where it was actually 95% is twice as bad as the other situation. So in the mathematical sense, scenario 3 is somehow twice as bad as scenario 4. But I don't really have a good intuitive understanding of that. So if somebody wants to like sit down and go into the tank and think about it and draw some pictures, maybe you can figure out why it's worse. So in this one, scenario 3 really is worse by a factor of 2, but it's not like in scenario 1 and 2. In scenario 1 and 2, it's worse by a factor of 10, right? So scenario 2 is 10 times worse than scenario 1 in terms of just these numbers. Okay. So yeah, what are the points? It's very tricky, especially near p equals 0 and p equals 1, and it's not even symmetrical. So it's quite a nasty loss function. Okay. Any questions or comments about that? So the thing I wanted to show you, now that you've appreciated that this is quite ugly, is that in logistic regression, the sigmoid function saves us. So this formula is very ugly, but when you do sigmoid, something very nice happens, is that the ugliness goes away. So I want to show you how that works. And this was in the video. There's like a detailed explanation and a detailed mathematical derivation. But I'm just going to give you the final answer and show you how it's useful. So this is for the mean squared error. So the mean squared error has this loss function. It's a y minus y hat squared. This is the loss. As function. Okay, yeah, so this is the loss. If you have some sample y and you estimate y hat, this is the loss function you get. And if you put in y hat is a function of x and some parameters beta, which is linear, so sum of xi beta I, that's what we said when we were doing linear regression. So in linear regression, we estimate as a linear combination of our x's with some parameters beta. And if the y hat depends on beta, then your loss function is a function of beta, right? So the loss function is a function of beta. You just put in y hat, it now depends on the parameters. And your job in linear regression is to find the best possible parameters, right? You're playing around with the parameters like we did in Desmos, right? You can change the slope, you can change the intercept, and you measure how good you're doing with the square loss, and you try to minimize it. How do you minimize something? Well, what's the way you learned in Calculus 1 to minimize something? You take the derivative, set it to 0, right? So the thing that we're interested in is the derivative. We're trying to minimize over beta. So you take the derivative with respect to beta. So you take the derivative with respect to beta, and what you get is a very nice formula. It's just this, y minus y hat, or what I'm calling f, multiplied by beta j. And by beta j, I mean xj. Okay, and let me make some samples here. So this is just one, but let's pretend there's n samples. So we'll do the sum from 1 to n, and then we're going to have an xi here, and a sum. Let me get rid of the semicolon. Xi, and this is xij. Okay, so what is this formula saying? The amount that you need to change beta j, or the derivative of the loss with respect to beta j, it depends on how far you are from the actual thing, right? Y is the true data point, f is your estimate. So the further you are, the bigger this is, times how much the ith data point has j in it, right? So this beta j, maybe I can do some colors. This j over here is the same as the j over here. It's telling you which feature to look at, the j feature. So if you're very far off, then your gradient is very big, and that's bad, right? If you're very close, then your gradient is small. You want to make the gradient 0. So there's a nice formula, and it really comes from the fact there is one factor of 2 that I'm missing, unless I put a half. Okay, let's do it without a half, so that the 2 will be here. And it really just comes from when you do the derivative of the square function. What's the derivative of x squared? It's just x, right? Very nice. Start with the square loss function, start with linear stuff, you get some nice linear thing. Beautiful. What happens if we do that for logistic regression? What happens if we do that for logistic regression? So in logistic regression, we don't have the mean squared loss, we have the cross entropy loss. The cross entropy loss. We have this thing, p log p hat plus 1 minus p log 1 minus p hat, right? With a negative sign in front of everything. We don't have a linear formula, we have a nonlinear formula with the sigmoid. P hat, right, is sigma of the sum, sigma of f of x beta, which is sigma, say xj beta j. So we have two nasty things, right? There's one is the cross entropy loss is quite nasty, and 2 is that we have the sigma, which is nonlinear. But if you plug in and you do a lot of work, a miracle happens. So here a miracle happens. Miracle. And sort of the nastiness from our cross entropy loss and the nastiness of the sigmoid cancel each other out, and you end up with a nice formula. This is why the logistic regression is so nice. What is the formula? So this is the loss. Let's call this the loss function. And it's going to, again, if you have parameters beta, it depends on the beta. Okay, so it was p log p hat. If you have actual data points y, then these p's are actually a sum over y, right? So it's y I, and then you do p hat of xi, p hat of xi, and you sum over all of them. So you sum over all your data points. Your data points yi can be either 1 or 0, but on average they're p, right? Which is where the formula came from. But when you do the actual derivative, you get this nice formula. The derivative of the loss, it's exactly the same thing as before, but with p instead of f. So you get yi minus p hat of xi, and then the same exact thing, just xij. So how much of the feature j appears in example x? And this is like why logistic regression is so nice, because it takes something that's nonlinear and it has the stupid, nasty cross-entry loss, and it makes it into something that's almost exactly like linear regression. So anytime you think about linear regression, you can also do, if you had a separate problem, you can think about logistic regression in the same way. And I want to show you like a little computer program where we use this formula for the gradient to find the parameters beta j for both, and you can see it's like almost the same exact code, and it runs the same way. And then I'm going to do like an example that's just like your project 1, but it's for a logistic regression thing on the Titanic data set. So we're trying to estimate if somebody survived or died in the Titanic, given a bunch of estimators. And you're going to see it's exactly like linear regression. So I guess that's the punchline, is logistic regression, even though it's got these multiple nasty things in it, eventually it turns into something just like linear regression. Any questions about this or the videos or anything before we, yeah.
First, I just wanted to know why we had we divided MSE by 2, and then you raised it.
Yeah.
So, and the second is that in the video I remember the sigmoid function was p divided by 1 plus p.
Yeah.
But when you wrote on Blackboard maybe a couple of minutes ago, you wrote like p divided by 1 minus p.
Those are the odds, right?
Okay.
And the odds are essentially the inverse of the sigmoid, right? So the sigmoid converts from log odds to probabilities. And I was when I was doing it earlier, I was converting from probabilities to odds, and it's exactly like the plus becomes a minus. Okay, so that's that one. Okay, this is a great question. Should there be a half here or not? So the first answer to the question is it doesn't matter, right? Because you're trying to minimize it. But the second answer to the question I think is interesting. So traditionally, sometimes people write it with a half. And there's 2 reasons you should write it with a half, and 1 reason you shouldn't write it with a half. The reason you shouldn't write it with a half is like you're just making it more complicated for no reason. So obviously don't write it with a half. The reasons you should write it with a half are twofold. One is, if the thing you actually care about is the derivative, then when you put in the half, it makes the derivative simpler. So you have a choice. Are you going to make the loss function complicated and the derivative simple, or are you going to make the derivative complicated and the loss function simple? And if you put a half, it makes the derivative simpler. The other reason there should be a half is there is a half in the formula for Gaussian random variables. So Gaussian random variables have this density function e to the minus 1/2 x squared. And this 1/2 something squared is exactly actually this 1/2 x squared from a Gaussian. So if there's a half in the Gaussians, there should be a half here. So that's one reason. Why is there a half in the Gaussians? It's exactly because of this derivative of x squared is 2. So yeah, you'll see it both ways. So let's be consistent. Let me leave it with no half so that you can notice this 2 and see like where it came from. The 2 came from the derivative of this. Over here, there is no 2 because it's somehow the derivative of sigmoid is somehow dealing with this cross entropy stuff in a complicated way. Yeah, great question. Anybody else? Okay, so let me show you the code that I want to show you guys. And that is, it's this notebook. It's called Gradient Descent for Linear and Logistic Regression. And so you can read it in the Colab. And I tried to follow my rules, which is that every code block needs to have a comment at the top. So every code block has a little comment, so you can see what's going on. And I tried to make sections. There's sections and subsections, so you can scroll through easily. So it should be pretty readable. I'll walk you through it now, but you can also read it sort of on your own time. So import the packages, create the data. This is the same data as we had last class, or 2 classes ago now, I guess. It's this class. And when we did it in class, we were saying, you can fit the sigmoid by just messing with these parameters, right? Like you change the A and the B parameter, and that will change where the sigmoid is. Okay, you don't want to flip it negative, right? You want to keep it like this, and you can try to fit really well. Before we do that, though, because we had a problem, right? This was where we were saying there's a problem because it's non-linear, and so you're screwed, right? When you try to map the zeros, they go to minus infinity, and the ones go to plus infinity. So when we did this in class, it was like, this is impossible, like you're doing something weird. And now we're going to see how logistic regression will save us. But before we even do logistic regression, let's just do regular linear regression and see how that would work in a computer. So if you do, let's pick some parameters. Qx plus w where Q and W are parameters, now I'm fitting a line. And the question you might ask is, what is the best possible value for these, right? And the way you measure it, again, you just use the mean squared error, and you play with the parameters to try to make the mean squared error as small as possible. And I'm going to show you how the computer program really does that in a way that is quite common nowadays. And that method is called linear regression. Okay, before we do that, I'm going to do the thing that you always have to do, which is set up a train test split, right? So this is the data. I'm going to divide the data into two parts. I'm going to divide it into a training set and a test set. So the blue is the training set and the red is the test set. And we're going to fit on the training set, and then we're going to see how we're doing on the test set, right? It's not fair to do it otherwise. Okay, and here's linear regression. It's exactly what's on the board, right? So our model function f is a sum of the parameters beta times the features x, and then our loss function is a squared function, and then the derivative is here. And you'll notice there's a mistake, right? Because I cheated, I made both of them nice, right? I didn't include the 2 and I didn't include the 1/2. You gotta put either a 2 here or a 1/2 there. But let's not worry about that. Okay. And so what I did is here I made functions. I made the function f, which is very simple. It inputs the x and it calculates this function f. That's not so complicated. And here's what it looks like, right? Here I just fed in some random numbers for the slope and the intercept, and you get some line. This is very not surprising. It's exactly the Python version of this green line we have over here. I will say there's one thing to keep your eye on that I've done so far, is I have a slope and an intercept, but the data only has an x, right? So where is the intercept coming from? In my formula for the function f, I did np.sum x times beta, axis equals -1, and that somehow automatically included an intercept. So does anybody know? There's one trick to get your linear functions to include an intercept, even though it seems like I didn't do any intercept, right? There's no intercept, right? There's no plus. You should say plus c or something, right? Where's the plus c? So where do you guys think the plus c is hiding?
You add mtx.
Yeah, say that again. I think you have the right idea.
Yeah, add an additional x.
Yes.
That x is just 1.
That's right. Okay, so this is exactly the common trick people do. Is these things are supposed to be the features of the x's, right? And in your housing data set, of course, you have hundreds of features of all the different parameters about the house. In this data set, it seems like I only have one feature, which is the x value. Okay, so I want to reconnect. But if you look at the data, it looks like there's only one feature x. But secretly, I added a second feature, and that second feature is always 1. So the data looks like x1, x2, x3, all the way up to xn, right? All the x values over there. But before I fed it into my computer program, what I did is I changed the data to have 2 features. There was x1, 1, x2, 1, x3, 1, and so on, all the way up to xn, 1. And by doing that, if you treat the 1s as a second feature, then when you do this linear combination, whichever beta goes with the 1s is going to be an intercept, because the x's always have a 1 in that position. So that's what I did, and you can actually see it in the code where I have this line where I do the features. And what I did is I took the x's and I took something np.ones that means make a vector of all 1s that is the same shape as the x's. And I stacked them together to make this. So this is exactly the line where the x's get converted to x's and 1s. And not only that, I did something else. I did standardize the x's. So before I put it into my features, I did this standardizing thing, which is instead of taking the raw values as written, I made it so the values are always approximately on the order of 1. And why is this nice? This is nice because it means the betas will be more interpretable, right? If these x's have values that are hundreds of thousands, then you're going to get a beta value that's 0.00001, and then you're going to be well, now what does that mean? Is that a small number? Well, no, actually 0.0001 is a huge number if you multiply it by 10,000. So this was in one of the videos talking about how the coefficients have units, and you got to be careful. So if you standardize, then you sort of have a handle on how big things are. And I know these x's are all approximately the same size. So what I actually did is I did these standardized x's. I'm going to call them bars. Maybe bar is the wrong thing, but that's what I did. Okay, so yeah, there were two tricks, standardizing and adding the ones. But once you do that, there's the model. And now we're going to ask the question, this line sucks. This green line is terrible right now. How can we improve the line? And it's going to go by the gradient. So we calculate the gradient, which was on the board a second ago, and is on the blackboard, or is in this notebook. So the gradient is the gradient with respect to the loss. And the idea of gradient descent is this very simple idea, which is that you can improve the value of a function by following the gradient. So to give you a silly example of this, imagine that this is a graph. This is a graph of the loss function as a function of beta. So it's important that you don't put this in your brain in the same place as these graphs, right? These graphs have x values and y values. This graph has beta values on the x-axis, and it has the loss, the value of the loss, as a function of beta over here. And our goal is to find parameters beta, like find the minimum of this thing. How do you find the minimum of something? Well, take wherever you are. You start here. Imagine you're in a big mountain, and you're standing here, and you want to find the minimum. Okay, if it was real life, you would look around and you go, okay, it's over there. But we're in math, we don't have eyes. No eyes. Okay. So what can we do? We look at our feet, and we figure out which direction is down. And the idea is you just keep stepping down. We're going to take a bunch of steps down. We're going to take a small step towards the gradient. So this direction is the gradient, or the gradient with respect to beta of the loss. And we're just going to repeat these small steps over and over again until we get to the bottom of the mountain. So because we don't have eyes, I don't know what the analogy of eyes is, all we do is we look at our feet and we just keep stepping down locally until we get to the minimum. And of course it can go horribly wrong. Like you can imagine, maybe, if the mountain looks like this, and you do this gradient descent thing, then you're going to take steps like this, and you're going to get stuck in this little spot. And because you have no eyes, you're going to think, oh, I'm done, right? I'm super happy, I'm at the minimum. But in fact, the minimum is over there, and you're here, so you're not doing very good. And so we're just going to cross our fingers and hope that this doesn't happen. So we're just going to pretend that this is not an issue, and just hope that it's fine. And the miracle is that it actually is fine. I don't know why this happens. So things can go wrong, and this is one of them. But we're just going to cross our fingers and hope that this works. Are there any questions about what this is? If you've never seen this before, maybe I went too fast. But if you've seen it a little bit.
This is going to be a numerical approach. So isn't there any analytical approach that we, let's say, find the exact beta by derivative and then plug it into the equation or whatever?
Yeah, so in the situation where you're doing linear regression, because everything is linear, everything is actually a big matrix equation. And so you can skip doing all this and change to just doing linear algebra. But that only works for linear regression. So as soon as you even do logistic regression, it's non-linear, and now you need some other method. And logistic regression is nice enough, it has some other things. But the reason I'm telling you guys this method now, and we're applying it to linear and logistic regression, is because later in the course we're going to do it for very complicated models where it's the only way to do it. So it's a really good method to know, and the reason I think this method has gotten so good is because it scales very well with computers. So if your computer gets twice as good, sort of like the smart way of doing it with pen and paper is still the same, but the computer way of doing it with gradient descent gets better. And that's why this has become very popular. So even like 10 years ago, people would like laugh at you. They'd be like, oh, don't do it that way, that's silly. But now this is what everybody does, and this is like how they make, like computer programs that can like chat and like generate images and stuff. It's all gradient descent. So that's why it's important to know. Yeah, great question. Any other questions about the method? So this is the philosophy. Let me show you how it works in the code. So we have our function, we have our test sets, and now we're just going to try to improve this green line. So the green line sucks. We're going to try to figure out, is it better to have the slope a little higher or a little lower? That's doing the derivative, seeing which way is up. And then we're just going to push it a little bit that way and see what happens. And the way we do that is I calculate the gradient. So this is the loss function, the mean squared error. And this is the gradient of the loss function. The gradient of the loss function. Okay, and it really is the formula that was on the board a second ago. It's the prediction error times x. So it's doing, really this formula. So it's a very simple formula, and it's simple to implement. It's one line of code, right? And now that you have the gradient loss, and you check it's the right shape, right? So here I'm doing two features, right? Because I have the x's and I have the 1. I have a beta 0 and a beta 1. That's why the shape of the gradient is 2. Now I'm going to do this gradient descent algorithm. And it really is just like the cartoon on the board. So the learning rate, the 0.01, that is how big the step size is, the little step. The number of iterations is the number of steps I'm going to take. Num displays, I'm going to pause and take a picture of what's going on 5 times throughout this 100, 200 step journey. And I'm going to print out the result. And I'm going to keep track of my loss. So the training loss and the test loss as I go. And hopefully it's going down, right? And it's important you do this with training loss and test loss because otherwise you won't know about funny stuff like this. So these histories are going to help us diagnose, are we doing it correctly? And what do we actually do? So we start with zeros. So I start with a flat line. So I start the betas at 0, 0, 0 slope, 0 intercept. I'm plotting everything, but really the core of it is this line labeled gradient descent. So all I do is every time I take a step, I just subtract from the parameters beta the learning rate, that's the step size, times the gradient. So that's doing this step in this direction. The rest of it is just bookkeeping, so I write down what happened. If it's time to print the picture, I print the picture. And then I do the final thing. And then I'm printing out the history of what happened. So what do you get after you do this? You get a nice plot like this. So the line started out as flat, 0 and 0 slope. After 40 iterations, it was this blue line. So you see the line went up a little bit, and then it went up a little more, and then it went up even more and more. But you can see the rate that it's going up is slowing down, right? So it started out going very fast, and then it slowed down as it gets close to the optimal thing. That's just like if you're in a big bowl and you're taking a step based on how steep it is. You're going to go faster at the beginning and slower at the end. And we can see our training loss and our test loss. It looks very good. It's going down. So our loss started out as 11. So how many units away from the true answer were we? Well, we were 11 square units away on average. And by the time we've done it 200 times, we're less than 1 away. So we're getting very close to this thing. Any questions or comments about that? I want to point out some things that can go wrong, and I did have to fiddle with these numbers. So before I uploaded this and saved it, I played a lot with this learning rate and these iterations. Let me show you what happens if you don't do that, and show you what can go wrong. So I have to rerun it because Google kicked me out. But so let's make the learning rate. Why not make a bigger step? Instead of doing 200 iterations where each step is 0.01, let's do 20 iterations where each step is 0.1, right? So 10 times bigger step, 10 times less steps should be the same, right? Let's run it and see what happens. Okay, this is what I came up with. That's not very good. It thinks the slope is negative. Here's what the loss function looks like. And look, it actually blew up after iteration 18. So the loss function was close to 0, and then I just went skyrocketed. This is 1 times e to the 32. So the loss went crazy. And what happened is, we took steps that were so big that we just stepped way over here to somewhere where things are going crazy, and everything went wrong. So we got to make it a lot smaller for things to work. So you do have to kind of tune this by hand, and there are smart ways to do it automatically, but let's try making it 0.05 and see what happens. Still exploded. But look, this time we made it to 100 iterations before it exploded, right? We made more iterations. There is some funny spot that I'm trying to get to where it does some funny stuff. Okay, so now it worked again. So this is actually fantastic. So this is much better than it was before, right? Like before the mean squared loss was like 1, now the mean squared loss is like 0.04. So by making the step size bigger, as long as it's not too big, you can get to the minimum faster. So this one looks very good, and look, we're finding a very nice line that cleanly cuts through the data. There is one thing that can happen that I thought I could get it to work, is sometimes you will oscillate back and forth. So you'll go like back, forth, and you can sometimes see that in the mean squared loss as it going up and down, up and down. Every other one is up and down. So that's something to watch out for. And yeah, for this model, it's very simple. For more complicated models, this is like an art to get good at this gradient descent based training. Okay, any questions or comments about this? Or
So in
yeah.
the situation do you go back and forth, you should only decrease the steps.
Yeah, so you should decrease the step because what's happening is you're overstepping the minimum. So if you make the step size smaller, then you'll be okay. And yeah, sometimes people do things on a schedule. So what they do is they make the first 10 steps big steps because you're like far away, so it's okay. And then they make the last few steps really small.
But okay, but we cannot understand if those 10 steps hit the minimum or not.
No, right. So the way you do it is you do 10 big steps and you see like, oh, it's fine for a while, and then it started to go up, down, up, down, up, down. And then you say, now make a small step. So this is like an art to doing it. And I've heard actually that you sometimes start low, go big, and then go low again. So it's like funny, like because if you're at the beginning, you're like really far away. So if you take a big step, you might go somewhere in the landscape that's like terrible. So you want to take a few small steps, get on the right track, and then you can like amp it up. So it is like an art to figure this stuff out. Yeah.
So this is when it's done for a single beta parameter, right? Or is this?
There's 2 beta parameters. There's the slope and the intercept.
Okay, but like let's say we had 20 parameters we're passing in.
Mm-hmm.
What does it? Do you have to do these gradients for each parameter, or does it? Like, does this can this process happen all at once for all the parameters?
It's happening all at once for all the parameters.
Okay.
This is a very good question. So when I wrote the formula of the derivative for 1 beta j. Okay. But you can make a vector version, and you would replace the left-hand side. It would, instead of being the derivative of beta j, it would be this upside-down triangle, the gradient. So it would be the vector of all of these things stacked together. Right? And the nice thing is the formula is so simple that when you stack everything together in a vector on the left-hand side, the right-hand side also stacks into a vector. This xij just becomes the vector x. And actually in the computer implementation, it's doing all of them at once. And you can see that if we go to the gradient, my little test here, this is like my little test to make sure everything is going correctly. It's outputting the gradient, and the gradient is a vector of size 2, right? 1 for beta 0 and 1 for beta 1. Actually here, this is a fun thing we can do. It's called linear regression. What is the linear in the linear regression? It doesn't mean it's a line. It means that the parameters are linear. So we can put in polynomials and see what happens. So let's go back to where we put the features in. Where did I put the features in? Here are the features, right? So I put in 1s and x's. Why don't I put in x squared as well? Okay, actually, okay, this will be a good lesson. Let's put in x cubed and as a feature. And so now everything should still work. But the gradient, for example, should be size 3. Okay, look, it's some crazy green curve, right? Instead of a line. Let's do this derivative and make sure it's working. So now the gradient is 3. So there's 3 features. Your first coefficient, your second coefficient, your third coefficient. And let me make this back to what it was originally and run it, and let's see what happens. Okay. So here, it exploded, even though I had the original settings. And actually, what you have to do to make a train, it seems like suddenly the step size is too big, even though it was the same thing as before. So let's make the step size much smaller, and I think it will eventually work. But no, it's still, so even if the step size is so much smaller, now it's, okay, so now it finally worked with a tiny, tiny, tiny step size. And let's look at the loss. The loss started huge and then started to come down, but it's like not changing much. So it's all around 3. And the fact that this is flat is kind of indicating we're not moving very much. So I probably have my step size too small. So I have to do it somewhere in between, and you can try it. And now it exploded again. And I'm going to tell you, the error, you think the error is here in the learning rate, but the error is actually way up here when I put in these features. Does anybody see what the error could be when I put in these features? So I added these x cubed things, yeah.
Yeah, you use the standard, but when you are going to make it a cube, you didn't use the standard.
Right, so this is actually what's happening, is the gradient descent, it's exactly the question you asked. It's trying to do all of the betas at the same time, right? So it has the same learning rate for this thing, the ones, and this thing, and that thing. And what happened is, I put in the x's. The x's on their own were not that bad. They were between, I think 0 and 14, right? They were originally, yeah, they were between 0 and 14. And then I standardized them to be between minus 1.5 and 1.5. So they were numbers like 1 to 10, reasonable numbers. But if you take numbers 0 to 14 and you cube them, now you have huge numbers. You have numbers like 1,000. And so what's going on, and this is why the gradient descent will never work as written, is the beta in front of the x's and the beta in front of these things are on like 2 different scales. So when you're trying to do the gradient descent and update them with the same step size for both, you can never satisfy both of them, right? Either the step size is way too small for this one, or it's way too big for this one. So if I put in a standardize on the x cubed, it should fix it. Standardize on the x cubed, that should fix it. So let's see if everything works now. And again, I probably don't need this insanely small rate now. Probably just need a moderately small rate. So now it's doing something quite nice. Okay, and again, I think the learning rate is a little bit too small. It's still only moved from here to here. So I can probably amp that up a little bit. But this is what it was originally set to, so maybe that just works. Yeah, okay, look. So it's figuring out a curvy line that goes through these now. It's still linear because it's linear in the parameters, right? That's the thing that is linear. Not the model, but the actual, how it depends on the parameters is all betas. Okay. Any other questions or comments? So this was all for linear regression. The thing I was trying to convince you guys is that logistic regression is exactly the same kind of thing, and that's what I'm going to do next. So in logistic regression, you have this p function. It's the same thing you had before, but you apply a sigmoid to it. And you use this other funny loss. But this funny sigmoid and the funny loss cancel out in some sense, and you end up with the same derivative. So when you go to write the code, it's exactly the same code. What did I do in the code? I just typed in this function, and I use that. So the fact that this formula is nice means everything is going to be nice, just like before. So same data as before. One thing you got to watch out for, when you're doing logistic regression, everything has to be between 0 and 1. So here I've changed the scale. In the previous problem, it was between 1 and 5, right? It was like this 1 to 5 star data. But I just subtracted 1 and divided it by 4 so that it was always between 0 and 1. This is the only change you have to do. Sigmoids always output things between 0 and 1. So if you don't do this change, then you're gonna be screwed. This is the only thing you gotta watch out for when you do logistic regression. Make your data between 0 and 1. So that was what I did. So I have this line, y01 value. That's the only thing that changed, y01 value. And it looks like this, it looks same kind of thing. And now I just have the same kind of stuff as before. And I'm even reusing the same function f as before. So p is sigmoid of f. And here's what it looks like. Here the sign was wrong, right? This is a sigmoid going the wrong way. We should have flipped it and had it go the other way. But the computer will figure that out. And so here's the cross entropy loss and the gradient, which are what we need them to be. Same formula as before. Like this line is copy pasted from the previous line. And the only thing that changed is the prediction. Instead of an f, it's a p. That's the only thing that changed. But the same exact code, it's like a copy paste of the code. It works, and you get nice things like this. Now it's finding the sigmoid that fits as good as possible. And if you plot the loss, it looks like this. And it seems to work. So, and again, I had to do some playing with the parameters, right? Because if you make it too big or too small, it explodes like before. But other than that, it works exactly the same way. The moral of the story is both gradient descent and gradient descent works for both logistic and linear regression in like the same way. And you can decide which one you want to use. So for this data, anytime your data is bounded and has like a definite lower and upper bound, you can always normalize it like this between 0 and 1 and get it to work. All right, any questions or comments about that? So this was the mathy like computer science take on linear and logistic regression. And I also have the data science approach, which I guess we'll mostly leave for next time, which is doing it on an actual data set. So this is logistic regression on the Titanic data set. So this is another Kaggle competition you can do where, let's open it up. Kaggle Titanic. Ahoy, welcome to Kaggle. Okay, so what we're trying to do is we're trying to predict who survived and who died on the Titanic, right? So we have a list of people and we have information about how they went on the Titanic. So how old they were, if they're male or female, how much they paid for their ticket, what cabin they were in and stuff. And so this is what the data set looks like. There's their passenger ID, whether or not they survived, that's what we're trying to predict, 0 or 1. Their P class is, are they a first class, second class, or third class passenger? So you're like rich or not rich, right? Male or female and so on. How many siblings they had on the boat, their ticket and stuff like that. For some of them, we know what cabin they were in. So I did some playing with this data. One thing I added in is I added in whether or not they're male or female as a number. Let me run this whole thing. And I did the log of how much they paid. So instead of looking at the number of dollars they paid, I did the log. And that's because some people paid a lot more money than other people. Some people paid like $5 and some people paid like $500. So this is, again, by taking the log, everything is closer together, right? Instead of being 5 and 500, now it's 7 and 5, right? Like they're a few numbers apart. And the first thing I did was I just explored the data, looked at the description, and then I did these seaborne plots. So I took all the nice things. My variables were, these are the variables I looked at. What class they were in, how old they were, stuff like that. And I did this seaborne plot with the color being whether or not they survived. So you get a nice thing like this, okay? And it looks ugly when I'm zoomed in here, so let me do it over here. This is the same exact code, but in GitHub, where it looks a little bit nicer for you guys. And so orange is people who survived, and blue is people who didn't survive. And you can see maybe which variables matter and which ones don't. So that's the hope with this kind of thing. Maybe you can like eliminate some variables. But I thought they all looked okay, and like I had some other ones on here that I deleted. But it looked okay, so what I did is I said, please do a logistic regression with everything, with all the variables, and tell me what you get. And so what I got is, these were the coefficients in the logistic regression, right? And these tell you how much things matter on this log odds scale. So for example, the biggest number here is male. If you're a male or not, you get a minus 2.6. And what that means is, if you're a male, your log odds of dying on the Titanic, or your log odds of surviving the Titanic go up by 2.6, right? So these have interpretations in terms of your odds of like actually living or dying, and I thought about it. I didn't write it down in the notebook. But what I did is I did make another one of these seaborne plots where I put the predicted probability as one of the variables. And you can see that if I predict that you survive, most people survive. And if I predict that you die, most people die. So it's pretty good. It's not bad. And now the question is, can I do better? So what I did is one of these variable selection things. So I tried all the subsets that include male. I thought being male or not seemed really important. And then I tried all of the possible combinations. So I looked at all the subsets of these things. P class, age, subset, how many parents you had, and your log fare. I went through every single combination, and I did a logistic regression. And this is the code. And look, I have this horrendous outputting all the possible variables, right? And what they are. And then at the end, I found the best one. And if you look at your accuracy, which one predicts the most accurately, it's age, siblings, log fare, and male. And if you look at which one has the best loss, using this loss function, it's your class, your siblings, your parents, your log fare, and if you're a male. So it's interesting that these are not the same. So I didn't know which one I needed to try. So I kind of tried both. And I did a regression. Remember, this was using a test set and a training set. So I had a test accuracy and a train accuracy. And then I did one with everything at the end here. Everything at the end. I tried both of these best combinations with the entire data set, and then I submitted it to Kaggle. So I ran it, and then I outputted the test set, and then I submitted it to Kaggle. And it turns out I did worse than the submission, which is just guess all the women lived and guess all the men died. Then you get 76% accuracy. I only got 75%. But this is where I stopped. So this is like logistic regression in action, and this should remind you a lot of your first project. And it should extra remind you a lot of your first project because I didn't do a good job organizing it. So I should add some sections here. I should clean up the code. And so in the last couple minutes, maybe let's make a little to-do list for me. And then I'll go home, and that's homework. I'll clean this up and make it like nice so that I get a good grade on the project. But this is like my rough draft, my very rough draft, and I just need to clean it up. So let's get, I'll make a little list on the board, and you guys can yell out suggestions, and I'll do them. And this is like really the difference between like math and data science, right? Is like this stuff. Like I've done the math, it ran, it works. You press go and it compiles, but like we need to explain it to people, and it needs to be, like a nice report. So what's on a to-do? Anyone have any suggestions? What do I need to add or take away? Yeah.
First, we need to add some comments on each cell.
Yeah, exactly. Comments on each cell. Yeah, exactly. Great. And I think this is a great rule that if every code block has to have a comment at the top, it'll help you decide what should I put in one block and what should be in two. Because very often I see people, they'll do like 3 related things in 3 blocks in a row. It should all be one block if it's all the same thing, and it should be like 2 blocks if they're different things, and tell me how they're different. So this rule about comments on each cell will help you organize and explain what's going on. All right, what else? Yeah.
Maybe take out a lot of the output that you don't need and only print the one that you finished.
Yeah, that's right. So like I printed out all this stuff that's like pages and pages and stuff, and then the only thing I used was the last guy, right? So why don't I print out just the last guy, and then if I really want to be fancy, I can make a variable that's like print everything, and then if it's true, then print everything. And then if the person running it wants to see everything, they can change the variable and run it, right? So print out only what you use. Only what you use. Okay. Anything else? I have the table of contents open as a, yeah. So it needs section right now. To get to stuff, you have to scroll through. Whereas if I had a nice table of contents, right now I have the Kaggle submission, you can jump straight to that, but nothing else you can jump to. And the other nice thing is that these things can get hidden. So if you have some technical stuff, like, oh, first I tried this, then I tried that, you can hide it quite easily if you put it in a section or a subsection. So sections and subsections. Okay, the other thing I'm missing, I didn't do all the parts that it told me, right? So in the assignment it says you have to have a part 1 that does the executive summary. You have to have the ethics thing. So it's actually missing some of the easy stuff. Easy. I'll put easy in quotes, right? Maybe it's not actually easy. And I verbally told you guys some of the interpretations, right? Like I told you, like male is 2.6. I said that out loud. I got to write that up in the interpretations part, or I don't get any credit for it. I guess I get, if you count the recording as the 5-minute video presentation, I get some credit for that, but you got to do all this stuff. Okay, I think that means the TV turning off means it's time to stop. So next class, I'll have a nicer version of this, and you guys, for the final project, I think will also be able to improve your things. See you guys on Tuesday then.